Well, the most basic version I know of is Feynman's version, which essentially says particles are particles and they hop from place to place with a particular probability. And the probability that a particle that's at some place will be at some different place later is given by a very simple rule. It uses a quantity called the action, which is to do with the mass of the particle and the time and the distance. So you basically calculate these little quantities, which are to do with something called the action, and you add them up. So if I start with an electron in one corner of the room, and I say, what's the probability at some time later it'll be somewhere else? Then at every point in the room, you can assign a probability that it will be there at a later point with one simple rule, and that's it. Now, this is called the path integral formulation of quantum mechanics. That underlies everything else. You can get the rest from that. So it's a simple rule. It says, what's the probability a particle will move from A to B?
The idea that you can't get something from nothing might not hold up when it comes to quantum physics. In the emptiness of space, which seems like nothing, you can actually create something by manipulating it in the right way. When two particles collide in this void, new particle-antiparticle pairs can appear. For example, if you try to split a meson's quark from its antiquark, new particles can emerge from the space between them. It's also possible to generate particles from a vacuum using a strong enough electromagnetic field, even if there were no particles present initially. This was once thought to be possible only in high-energy physics labs or extreme cosmic environments, like around magnetars or in high-energy nuclear collisions. However, recent experiments in simple lab settings using graphene have produced these particle-antiparticle pairs, confirming predictions made by physicist Julian Schwinger over 70 years ago. Even well-known physicist Brian Cox has supported this concept in quantum theory in general. The Schwinger effect shows that the universe can indeed create something from nothing.
Even in 1897, the importance of the beginnings of particle physics, the discovery of radioactivity, was recognized. And in fact, if you then look back from the point of view of the 1920s, this is an era, 20 years, part of a scientific lifetime, when we get very quickly radioactivity, we get quantum theory, we get relativity, the foundations of modern physics. And I found another remarkable quote, actually, from Ernest Rutherford, from Pice's book. It's a wonderful book if you haven't read it. Looking back in 1924. So this is really 20, 25 years after the beginnings of modern particle physics. Rutherford wrote, "The year 1896 marked the beginning of what has been aptly termed the heroic age of physical science. Never before in the history of physics has there been witnessed such a period of intense activity when discoveries of fundamental importance have followed one another with such bewildering rapidity." That's looking back at that period, the turn of the 20th century. I actually genuinely think, and I wonder whether many of us do, that we're living through the beginnings of such a period now. The level of precision with which we understand the universe at some level is quite remarkable, but also the number of experimental results now that are beginning to say that there needs to be a real shift in our understanding are also building up one after the other. We've seen, of course, dark matter. We're looking at things like the hierarchy problem, dark energy, of course. All those results seem to point to a revolution in our understanding of the universe because of the experimental data that we are gathering in both cosmology on the largest scales and in particle physics at the smallest scales.
The universe has always fascinated both scientists and philosophers, leading to the deep quest to understand its core aspects. While our senses provide a view of the world, this view can sometimes be misleading. Modern science offers a clearer picture. Advances in physics have shown that our everyday experiences don't always reveal the true nature of reality. Instead of thinking of the universe as made up of fixed objects, we now understand it as dynamic and constantly changing. Space isn't empty, but filled with quantum fields, which means it holds hidden energies and phenomena that can appear under certain conditions. The universe is always in motion, with everything continuously evolving rather than staying the same. By studying the basic principles and laws of the universe, we can predict future events and understand the past. The goal is to find out what makes up the universe, how these components interact, and solve the equations that predict future outcomes. Although this makes the universe conceptually understandable, the strange nature of quantum mechanics can still be hard to grasp. In the universe we live in, it's impossible to create or achieve absolute nothingness in a truly complete sense. At the most basic level, everything consists of individual entities, or quanta, that cannot be further divided. These elementary particles include quarks, electrons, the heavier cousins of electrons known as mu and tau, neutrinos, their antimatter counterparts, photons, gluons, heavy bosons, and the Higgs boson. Even if you were to remove all of these, the space that remains wouldn't be truly empty in a physical sense. First, quantum fields still exist, even when no particles are present. Just as the laws of physics can't be removed from the universe, quantum fields can't be stripped away. The vacuum is a state of the lowest possible energy, but not zero energy. This vacuum is filled with quantum fields, which can create particle-antiparticle pairs that momentarily appear and vanish. Additionally, no matter how far we move any sources of matter, two long-range forces remain: electromagnetism and gravitation. While we can create conditions that ensure the electromagnetic field strength in the area is zero, we can't do the same for gravity. So, space can't be entirely emptied in any absolute sense. Even for the electromagnetic force, if you completely eliminate the electric and magnetic fields in a region of space, experiments have shown that empty space isn't truly empty. Even in a perfect vacuum, where all particles and antiparticles are absent and the electric and magnetic fields are zero, there's still something present in the so-called maximum nothingness. If you place a pair of parallel conducting plates in this area, you'd expect them to only experience the force of their mutual gravitational attraction. However, the plates attract each other much more strongly than gravity alone would suggest. This phenomenon is known as the Casimir effect, and Steve Lamoureux demonstrated it in 1996, 48 years after Henrik Casimir first calculated and proposed it. Now, let me explain the Casimir effect. Henrik Casimir's idea for the experiment was straightforward. Place two uncharged metallic plates very close together in a vacuum and wait. Without any external force, no gravity, tension, or magnetism involved, the plates will naturally be drawn together. But why does this happen? The explanation lies in the quantum nature of the vacuum. What seems like empty space is actually filled with fluctuating electromagnetic fields, creating a sea of virtual particles that constantly appear and disappear. When two conductive plates are placed close together, they limit the wavelengths of these virtual particles between them compared to the space outside. This creates a pressure difference, which results in an attractive force that pulls the plates together. We don't usually notice or experience the Casimir effect in everyday life, but it becomes crucial when dealing with micro and nanoscale devices. When designing micro and nanoscale machines, engineers and scientists must consider all forces that could impact the performance and behavior of these tiny devices. The Casimir effect is one such force that, while insignificant at larger scales, can significantly influence micro and nano-level devices due to the close proximity of their components. For instance, researchers have developed microscale sensors that can detect and analyze chemical flow with molecule-by-molecule precision. These sensors depend on the exact movement and interaction of their components. If the Casimir effect isn't accounted for during the design process, the unintended attraction between parts could lead to malfunctions or inaccuracies in sensor readings. In 1951, Julian Schwinger, one of the co-founders of the quantum field theory, which explains the behavior of electrons and electromagnetic forces, provided a thorough theoretical explanation of how matter could be created from nothing by applying a strong electric field. While Fritz Sauter, Werner Heisenberg, and Hans Euler had introduced this concept in the 1930s, Schwinger conducted the detailed work to define the conditions under which this effect would occur. Consequently, it's mainly known as the Schwinger effect. Typically, we experience quantum fluctuations in empty space to excite any and all quantum fields present. The Heisenberg uncertainty principle states that certain pairs of quantities cannot be precisely known at the same time. These pairs include energy and time, position and momentum, orientation and angular momentum, voltage and free electric charge, and electric field and electric polarization density. While the uncertainty principle is often discussed in terms of the first two pairs, its implications extend to the others as well. Remember, any force can be described by a field, where the force acting on a particle is equal to its charge multiplied by a property of the field. When a particle moves through a region where the field is non-zero, it may experience a force depending on its charge, and at times its motion. The stronger the field, the greater the force, and therefore, the more field energy is concentrated in that area of space. Even in completely empty space, with no external fields, there's still a small amount of non-zero field energy present in any region. Since quantum fields are everywhere, according to Heisenberg's uncertainty principle, there will always be an inherently uncertain amount of energy in that region over any given period of time. The shorter the time we observe, the greater the uncertainty in the amount of energy. Considering all possible quantum states, we can imagine fluctuating fields and particle-antiparticle pairs that intermittently appear and vanish due to various quantum forces in the universe. Now let's increase the electric field. As it strengthens, what happens? To simplify, consider a meson composed of a quark and an antiquark. They're bound together by the strong force and gluons. Quarks come in 6 flavors: up, down, strange, charm, bottom, and top. Antiquarks are simply their opposites with reverse charges. Sometimes a quark and an antiquark in a meson have opposite charges, either plus 2/3 and minus 2/3 for up, charm, and top, or plus 1/3 and minus 1/3 for down, strange, and bottom. When an electric field is applied to this meson, the positive and negative ends will be pulled in different directions. If the field is strong enough, it can separate them enough to create new particle-antiparticle pairs from the vacuum between them. This results in 2 mesons rather than 1, with the additional mass coming from the energy in the electric field that originally separated the meson. Now consider an extremely intense electric field, far stronger than what we can generate here on Earth. Picture condensing a full coulomb of charge, about 10 to the power of 19 electrons and protons, into 2 tiny spheres, one positively charged and one negatively charged, separated by just 1 meter. In this scenario, the quantum vacuum would be highly polarized, with a substantial separation between positive and negative charges. If the electric field is strong enough, it can create a virtual particle-antiparticle pair of the lightest charged particles, electrons and positrons. If the field's force separates them sufficiently, they may not reunite and annihilate. Instead, they become real particles, extracting energy from the electric field to maintain energy conservation. This process creates new particle-antiparticle pairs, with the energy required for their formation, according to E equals mc squared, reducing the strength of the external electric field. This phenomenon, known as the Schwinger effect, has not yet been observed in laboratory conditions. It's primarily believed to occur in extreme astrophysical environments, such as near black holes and neutron stars. However, these locations are so distant that the Schwinger effect remains theoretical. On Earth, the strongest electric fields we can generate are in laser laboratories, but even with the most powerful lasers, they fall short. Typically, in conducting materials, only certain electrons can move freely and contribute to conductivity. If exceptionally strong electric fields could be created, it would allow all electrons to flow. In January 2022, researchers at the University of Manchester utilized a sophisticated setup with graphene, a robust material composed of carbon atoms, to observe the Schwinger effect with a relatively small and manageable magnetic field. They detected the creation of electron-positron pairs in this quantum system. Graphene is notable for its unique properties, particularly its behavior as a 2-dimensional structure. The reduction of dimensions restricts the quantum particles' options and the quantum states that they can occupy. In a study, researchers used a graphene-based superlattice, which consists of multiple layers of materials arranged in periodic patterns. By applying an electric field, they observed unusual behavior. Electrons flowed not only from the highest partially occupied energy state, but also from lower, fully filled bands. This led to several unique phenomena, including the first observation of the Schwinger effect. Instead of generating electrons and positrons, it produced electrons and their condensed matter counterpart, holes. Holes represent missing electrons in a lattice and move in the opposite direction of electrons. The observed currents could only be explained by the spontaneous creation of electrons and holes, aligning with Schwinger's predictions from 1951. Exploring the universe involves various techniques, and quantum analog systems are among the most effective tools for studying exotic physics. These systems use mathematical principles to describe otherwise inaccessible physical phenomena, but they can be created and examined in a lab environment. Testing the Schwinger effect in its pure form is difficult. Yet graphene's exceptional properties, such as its ability to handle extremely high electric fields and currents, have allowed this effect to be observed for the first time in this specific quantum setup. As co-author Dr. Roshan Krishna Kumar explained, when we first observed the extraordinary properties of our superlattice devices, we were amazed, thinking it might be a new form of superconductivity. Although the behavior resembled that of superconductors, we soon realized it wasn't superconductivity, but rather something related to astrophysics and particle physics. It's fascinating to see such connections between different fields, with electrons and positrons, or holes, appearing seemingly from nowhere, pulled from the quantum vacuum by electric fields. The universe often reveals the seemingly impossible, creating something from nothing. We don't inhabit a universe where matter simply drifts into an empty void. Rather, we live in a universe filled with energy fields that extend throughout space and interact with each other, creating everything we perceive. The idea of nothingness, the boundless void, and death is surprisingly unsettling. William Shatner, at the age of 90, ventured into space expecting to uncover the universe's mysteries, but instead encountered a stark, empty expanse. All I saw was death. I saw a cold, dark, black emptiness. It was unlike any darkness you can see or feel here on Earth. It was profound, engulfing, and all-encompassing. However, this so-called void wasn't truly empty. It was a vacuum, where, at the moment, countless processes were occurring beyond Shatner's view. Quantum field theory is one of the most successful theories in physics, celebrated for its precision in predicting various experimental results. This theory suggests that our universe isn't made up of matter floating in empty space, but rather consists of energy fields that fill space and interact with each other, leading to the formation of everything we see, including ourselves, as part of these fields. Some physicists compare these fields to fluid, similar to water in a swimming pool, while others see them as spaces filled with varying energy levels, like a field of distributed heat. These fields are always in motion due to quantum fluctuations, brief changes in energy that resemble ripples caused by external forces exciting the particles within the field. For example, an electromagnet can alter an electromagnetic field. Even in their lowest energy state, known as the vacuum state, these fields are active. Pairs of positive and negative particles constantly borrow energy from the vacuum, briefly appear, and then disappear, returning the energy to the vacuum. These short-lived entities are called virtual particles. When a particle is excited or reaches a higher energy state, it produces ripples or waves that generate elementary particles, which are not canceled out. These particles interact with each other to form the physical world that we experience. The type of particles created depends on the specific field. Various matter particles are associated with different fermions, such as electrons, up quarks, down quarks, all fundamental components of atoms, and neutrinos. These fermions interact through three types of fields: electromagnetism, with photons as its particles, the strong nuclear force, featuring gluons, and the weak nuclear force, with the W and Z bosons as its particles. According to Cambridge theoretical physicist David Tong, without these force fields, matter particles would drift aimlessly in the universe, lacking interactions and interesting behaviors. Then there's the Higgs field, which Tong compares to molasses spread throughout the universe. This field gives mass to other particles, preventing them from moving at the speed of light. Tong notes that this analogy is imperfect because it suggests friction, whereas particles interact with the Higgs field in various ways. All fields, including those of matter and force, are present everywhere, but interact differently. Some particles in these fields ignore each other, while others interact, leading to reactions and complex structures. The interplay of these fields encompasses everything we know and observe, as well as much that remains beyond our current understanding. Interestingly, the formation of particles that make up matter is an exception. For example, an atom forms when there's enough energy in the quark fields to produce quarks that are not annihilated by antimatter quarks, although the exact reason for this is not fully clear. Gluons, which are associated with a strong force, combine with two up quarks and one down quark to form a proton. Then, gluons bind protons with neutrons to create a nucleus. Physicists believe that the visible universe consists of remnants that survive the ongoing creation and destruction of virtual particles. However, the particles that constitute dark matter remain a separate and distinct issue. Even though the universe is filled with virtual particles, it doesn't completely rule out the idea of nothingness. First, there's the enigma of the state before the Big Bang, a concept that remains beyond our grasp. Additionally, this nothingness, characterized by vast fields of quantum energy, seems to be the source of the fundamental elements, matter and force, that eventually formed our world. Physicists are still puzzled as to why certain elemental particles survived after the Big Bang. Theoretical physicist Lawrence Krauss, in his book, A Universe from Nothing, proposed that the answer might lie in the unstable nature of nothingness itself, which leads to the emergence of elementary particles. Another intriguing idea is that the entire universe might be a massive virtual particle. The vacuum genesis hypothesis suggests that the universe began as a significant fluctuation in the void that existed before it. While this remains unproven, it's a thought-provoking notion that ultimately, everything, including you, me, and the entire universe, might just be a vast expanse of nothingness. No matter how clearly you might envision an empty universe with nothing in it, that idea doesn't match reality. The principles of physics make it clear that a truly empty universe is impossible. Even if we consider only the zero-point energy of the quantum vacuum, some form of radiation will always be present. The universe has never been completely empty, and as long as dark energy persists, it will never be. While we strive to understand the universe as thoroughly as possible, we must remain modest in the face of the vast cosmic mysteries. So here's my advice. Embrace the curiosity that drives us to explore, question, and discover the unfolding mysteries. That's it for this video. I hope you enjoyed it. Thanks for watching, and please stay tuned for more videos.